Hi everybody. Okay, so this video is going to be your little how-to to solving limiting reactant problems using a BCA or a before change after table, just in case you need a little refresher. So, what you kind of want to do to start any chemistry problem like this is go through and make a list of like what you know. So let's read this problem together. Serena's working in the lab and wants to make some solid silver. She mixes 45.53 grams of silver nitrate with 6.56 grams of solid copper. Determine the moles of all species at the end of the reaction. So if I list this out, it tells me to determine moles of all species at end of the reaction. And we assume the reaction goes to completion. So to kind of decide, is this a limiting reactant problem or not, you have to ask yourself, am I given measurements? Am I given values for more than one reacting species here? And the answer is yeah, man. So you have 45.53 grams of silver nitrate, that's one reactant, and 6.56 grams of solid copper. You're the reactant. So if you are given more than one measurement for your reacting species, automatically this puts you down the limiting reactant track of how to solve this problem. So first things first, you have to start out with a balanced chemical reaction equation. So we have to figure out what the heck Rena's going to make. So it tells us that she's starting out with silver nitrate. Silver has a +1 charge, nitrate has a -1 charge. So when we crisscross or balance our charges out, we should end up with the formula silver nitrate AgNO3. So she's mixing this with 6.56 gram of solid copper shot. So copper just has the formula Cu elemental copper. So if we figure out what type of reaction this is, that'll help us predict our products for it. Well, I've got an elemental metal and I've got an aqueous ionic solution, which means that this is going to be metallic single replacement. So to figure out if this reaction actually happens, we do have to consult our activity series. Our elemental metal copper wants to replace the silver in solution. So to figure out if this actually happens, we take a look at the activity series to see if these two things are going to swap places. It would be wild if the answer was no, because then this video would essentially be over and it would not have accomplished the goal of teaching you how to do limiting reactions with the BCA table. So you should realize that, yeah, this is going to switch. Copper is going to in fact be more reactive than the silver and is going to kick it precipitate it out while copper dissolves into the solution. So when I do that, silver is going to get kicked out as elemental silver. So I'm just going to have solid silver, and the copper is going to dissolve into solution. Copper, its most common oxidation state is 2+, so we are going to assume that it has a 2+ charge. So copper 2+, nitrate still has 1-, so when we balance out those charges, we're going to end up with CuNO3 2 dissolved in solution. So last step is to balance this out. If I put a 2 here and I put a 2 here, I've got a balanced chemical reaction equation. Amazing. Okay, so now next step is I have to actually figure out what the heck my limiting reactant is. But I am giving these measurements of my reactants in masses. Masses are never, ever, 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 ever comparable. The only thing we can actually compare here is moles. So I know that I'm given 45.53 grams of this. I know I'm given 6.56 grams of this. I know at the end of this, I am tasked with finding the moles of all reacting species. So to figure out what my limiting reactant is, I first convert to moles. So 45.53 grams of silver nitrate. And if I want to convert this to moles, I have to think about my mole map, right? I'm starting with mass, grams of some substance. I need to get to moles of another substance. Okay, mass and moles, molar, mass. So I'm going to use the molar mass conversion factor to help me out. I need to get rid of this unit here to convert to moles. Remember that you can only change one thing at a time in each of your conversions. So my first step is to keep the same substance, silver nitrate, but convert it to a different unit. So I want to get rid of the grams of AgNO3 and I want to convert it to moles of AgNO3. Remember that molar mass is defined as the amount of mass per 1 mole of every substance, so it must be a 1 in front of that number. And then I need to actually calculate the molar mass for silver nitrate, which I did earlier, and it ended up with 169.874 grams. All right, so this will cause me to end with moles of silver nitrate. My grams will cancel out. So now I just need to plug it into my calculator. And I end up with 0.2680 moles of silver nitrate. It's good to kind of keep a decent amount of decimals here. You don't want to round off for sig figs until the very end of the problem. So for right now, I'm going to keep 4 decimals because it'll keep me pretty accurate. So that's how many moles of silver nitrate I'm starting out to work with. I know that I'm starting with a mass of 6.56 grams of copper. I also want to convert this to moles, which means my setup is going to be the exact same thing. I have moles of copper on top, and I have the molar mass of copper, 63.546 grams of copper that are going to go in the denominator. So my units of grams will cancel out. When I plug this into my calculator, I end up with a value of 0.1032 moles of copper. All right, so now we stop and ask ourselves, what's our mole ratio? How much of each of these substances am I going to use every time this reaction runs? So if I look back up at my balanced chemical equation, I need 2 moles of silver nitrate for every 1 mole of copper every time this reaction runs. So I can't just leave my moles the way they are to compare them. I have to now compare them according to the mole ratio, how much I'm going to use every single time. So for silver nitrate, I'm going to use this many moles, or I have this many moles to start with, sorry. But every time I run this reaction, I use 2 moles of silver nitrate per every 1 reaction. For copper, my mole ratio, or my balanced chemical equation tells me I only use 1 mole. So every 1 reaction, I'm going to use 1 mole of copper. So all I have to do now is take my moles of silver nitrate, and I'm going to divide it out by 2 to figure out how much I use per every reaction, and I end up with 0.1340 moles. For copper, since I'm just multiplying by 1, 0.1032 moles. So kind of close, but this one up here ends up being smaller. Because this value is smaller here, it tells me that silver nitrate, oh wait, what? That number's not smaller. I'm so silly for this one. These numbers are very close, but this one is smaller, I meant to say. So this tells us that copper is the limiting reactant. That's what I get for making a video later in the day. Crazy me. All right, so because copper is now my limiting reactant, I can kind of finish off the rest of this problem with that in mind. So I'm starting with this value of my moles of copper. What I'm asked to solve for is moles of species at the end of the reaction. If you are asked to solve for the values of like more than one substance in a stoichiometry problem like this, a BCA table really is your best bet. It's kind of the easiest way to track how everything in your reaction is changing over time, so it's something that I always kind of recommend doing. So a BCA table stands for before change to after, and what you're tracking is how much of your substances you are using every reaction over time until something runs out. So to set up your BCA table, you rewrite your chemical reaction equation. So I'm going to rewrite that right here. And then you set yourselves up your little table structure. So you have your B for before, C for change, and then I'd like to draw myself a little dashed line for after. So let's think about our system before the reaction has actually occurred. Before the reaction has occurred, we already calculated how many moles of each species we have. We know that we have 0.2680 moles of our silver nitrate, and we have 0.1032 moles of copper. I'm pulling these numbers from right here when I originally converted to the amount of moles I had for the amount of mass that I had. Before the reaction occurs, before I mix these two things together, how much solid silver should we have? 0, Miss Lambert. Yeah, for jerseys. If your reaction hasn't happened yet, you don't have any product, right? So the answer for both of those is going to be 0 moles. You don't have anything yet. All right, so now our change section. So here's really what your change section of the table is actually talking about. If you had the ideal ratio to run this reaction, you would need 2 moles of silver nitrate, 1 mole of copper, and you would produce 2 moles of silver and 1 mole of copper nitrate. I'm pulling those numbers from the coefficients in the balanced chemical reaction. However, I do not have 2 moles of silver nitrate. I have 0.2680 moles of silver nitrate. I do not have 1 mole of copper. I have 0.1032 moles of copper. So this change section is basically setting yourself a proportion. Proportionally, how much of my silver nitrate am I going to use so my ratio remains the same every time I run this reaction? So I know that when I run this reaction, I use twice as much silver nitrate as I do copper. So I'm going to say the amount of substance that I'm going to use, I'm going to label variable X. And over time, because we are using these reactants, they are decreasing in the amount that we have available. So I'm losing some amount of silver nitrate, so minus X. I'm losing some amount of copper, minus X. But I lose twice as much silver nitrate as I do copper every time the reaction runs. So this X number represents proportionally how much your system is losing or gaining in moles as the reaction occurs. So now let's think about our products. Well, over time, we should be making product, right? So we're going to be adding some amount of product to our system. I add some amount of silver, I add some amount of copper nitrate, and I'm going to make twice as much silver as I do copper nitrate. So what your change section here is now set up for is saying you started with some amount of moles of your substance. You are either losing or gaining a proportional amount, and after the reaction has finished, these two numbers added together will be equal to your after amount. I did forget to mention this, but in a BCA table, you want to make sure that you are only including moles because your moles are your proportional values. You can compare moles, you cannot compare masses. So we're going to make ourselves a little equation for each of these sections. After the reaction, we started with 0.2680 moles of silver nitrate, and we're going to lose 2x amount. So after, we are going to have this value left over. For copper, we started with this many moles, and we're going to lose some amount of it over time. For silver, we are going to make 2x amount. We're going to make double the amount of silver as we are copper nitrate, and we're going to have x amount of it over time. So at this point, you've set yourself up some what are they called? Not equations, expressions, maybe? You set yourself up some expressions that kind of show how many moles of substance you're going to have over time, but we have to solve for this X value. How we do that is we remember our limiting reactant. Our limiting reactant says at the end of this reaction, assuming the reaction goes to completion, all of it will be used and we will have none of it left over. Our copper was our limiting reactant. So what we can say is this value right here should be equal to 0 because at the end of the reaction, no copper will be left over. So I just rearrange my equation using some quick little algebra, add x to the other side, and I'm going to end up with x being equal to this value right here. Now that I know x, I can plug it back in and just figure out how many moles of every substance I'm going to have at the end of this reaction. So, moles at end of reaction. So for my silver nitrate, I just simply plug in this x value, 1032, and that's going to tell me that at the end of this reaction, I'm going to end up with 0.016, or 616, sorry, moles of AgNO3 left over. For copper, I will end up with 0 moles left over because this one is my limiting reactant. At the end of my reaction, I'm going to make 2x moles of silver. So plugging that in my calculator, I end up with 0.206 moles. Sig figs tell me I only need 3 significant figures at the end of this problem, so I'm rounding everything off to 3. And then for copper nitrate, this is equal to x. I'm going to make x amount of it, which means I'm going to make 0.1032 moles of this solution at the end of the reaction. So this is your basic structure for how to complete a BCA table problem for limiting reactants. Start by writing your balanced chemical equation, determining your limiting reactant by converting to moles and comparing which reactant has a smaller value of moles. Set up your BCA table to plug in how many moles of things you had before. Proportionally figure out how much you are losing or gaining. After, you set your limiting reactant equal to 0 and solve for x, which represents a proportional amount of moles. And then you plug in x for all of your values here, and that tells you how many moles you have left at the end. If your problem asks you to solve for masses at the end of this, no big deal. All you need to do is one last conversion step where you take any of these values of moles that you have left over and convert back to grams using molar mass. All right, hope you found this helpful.